Hey physics fans, welcome back to lesson 13, second video. Now for the second video, we're going over chapter 10.5, which covers moments of inertia. Now inertia was first used by Johannes Kepler, and it literally means laziness in Latin. So it's how hard it is to get something to accelerate. For a moment of inertia, we're talking about rotational inertia, so how hard it is to angularly accelerate something. Now, the inertia is dependent on the mass of an object, and it's dependent on how far the object is from some axis of rotation. So if we are to find the moment of inertia for a series of point objects, we need to know the mass of each point object and the distance from some axis of rotation. Once we know those quantities, then the inertia is simply summing all of the individual masses and their distances squared from some axis of rotation. Now, most objects are not a series of point masses, or at least we don't see them that way. They're continuous, rigid objects. Continuous meaning that the entire object has no discontinuities, and rigid meaning that the object doesn't deform as you're moving it around. So to calculate the inertia of a continuous rigid object, we have to take the sum of every infinitesimal point mass on that object with how far it is from the axis of rotation. In doing that, we take the integral of our radius squared for some mass element. Now for common shapes, some spheres, cylinders, thin long rods, we've derived those equations for you. They're both in the textbook in figure 10-20, and they are on your physics reference card. Now for many objects, we don't rotate the object about its center of mass. We displace it and rotate it about some other axis. And for that, we use the parallel axis theorem. Now the parallel axis theorem takes into account both the inertia about the center of mass, which we derived on the reference card, and the total mass of the object times how far it's displaced from its original axis of rotation squared. So let's go through an example. If I were to take a sphere and I were to rotate it about a parallel axis. Now once again, what that means is I'm not rotating the object about its own axis of rotation. Instead, I'm rotating the object about an axis that is parallel to its original axis going through the center of mass of the object. That distance from the parallel axis to our axis through the center of mass is our quantity d. So using the parallel axis theorem, we first figure out the inertia about the center of mass for our uniform solid sphere, which is 2/5 times the mass of the sphere times the radius of the sphere squared, and we add that to the mass times the horizontal displacement from the axis through the center of mass to our new axis of rotation squared. And that will give us the total inertia of our solid sphere rotating about a parallel axis. Now just remember, if you have an object that's rolling, it is rotating about its center of mass. So you don't have to use the parallel axis. That's a common misconception that physics students have. Now our last thing we're going to go through is the total inertia of a system. Remember, if you have multiple point masses, then you add up the individual inertias of each point mass. So if you have a continuous rigid object that consists of more than one shape, you can also add up the individual inertias from each shape, meaning that the total inertia is equal to the sum of all of our individual inertias. That's it for today's lesson. See you in class. Make sure you let your instructor know if you have any questions.